Can you see the slide? Yes, is the slide visible?
Yes, sir.
So the next example goes like this. Two DC shunt machines are tested using Hopkinson test with following data. The line current drawn from the supply is 18 amperes at 220 volts. The motor current is 110 amperes and field current are 2.5 amperes and 3.1 amperes. The armature resistance is 0.05 ohms. Find the efficiency of motor. Okay, here we need to find efficiency of motor. So when you see this part of statement, it appears the first connection where the fields are connected in shunt with the armature. When we see the second part of this statement, also find efficiency of motor and generator if the fields are separately connected across the supply with the line currents remaining the same. Okay, so whatever the line currents the motor and generators are taking now, with the same line currents, what will be the efficiency of motor and generator if the fields are connected separately to the uh, supply? Okay, so first part we have to do the calculations with the first connection, keeping the field winding in parallel with the armature. Second part we have to do the alternative connection and find the efficiencies. But in first case we need to find efficiency of only the motor. Okay, so solution. First, uh, we'll take that fields connected. Fields connected across armature. Fields connected across armature. Okay, so with that, we'll do the circuit diagram. For every solution, you should draw the circuit diagram. Whether it is Finburns test or Hopkinson test or other test, what we do. Okay, so supply voltage is 220 volts. Okay. So field currents are 2.5 amperes and 3.1 amperes. So this is 2.5, motor field current will be low and generator field current will be more, 3.1 amperes. Okay. The line current drawn from the supply is 18 amperes. Okay. Then the motor current is 110 amperes. So this is 110. Next, armature resistance is 0.05. So here we can write, okay, I1 is equals to 18 amps. I1 plus I2 is equals to 110 amps. I3 is equals to 2.5 amps. I4 is equals to 3.1 amps. And RA is 0.05 ohms. V is 220 volts. Anything else given? So we know these things. Therefore, I2 is equals to 110 minus I1. That is 110 minus 18, which is equals to 92 amperes. Okay. Next, we will find out the stray losses. So stray losses, WST is equals to, I will write directly. Okay, V into I1 minus I1 plus I2 minus I3 square RA M plus V into I3 plus I1 plus I2 square RAG. Sorry, not I1 plus I2 square, it is I2 plus I4 square RAG plus V into I4. There is no brush drop given, so we will not consider it. That's it. So this is equals to 220 into 18 minus. It is, I will write it separately here because many times I have to use I1 plus I2 minus I3 is equals to, so 110 minus 2.5. So this is 107, sorry, 107.5 amperes. So this is IAM. IAM is equal to I1 plus I2 minus I3. And IAG is equals to I2 plus I4. So that is 92 plus 3.1, which is equals to 95.1 amperes. Okay. So this will be 107.5 square into 0.05 plus V into I3, 220 into 2.5 plus 95.1 square into 0.05 plus 220 into 3.1. So WST is equals to
1697.987.
1697.987 watts. So therefore stray losses in each machine WS is equals to WST by 2. So 1697.98 by 2. So 848.99, that is 849 I will take. Okay, 849. If motor efficiency. Motor input is equals to V into I1 plus I2. That is 220 into 110. Pn is equals to 24,200. watts. Motor losses. Wg will be equals to. Okay. It is, sorry, Wm is equals to IAM square Ra plus V into I4 plus Ws. Armature copper loss plus field copper loss plus stray loss. So IAM square is 107.5 into 0.05 plus 220 into 2.5 plus 849. So Wm is equals to
197.8.
yes
1972.81.
1972.85. 1972.85. All are getting same?
Yes, sir.
Yeah. How much? How much you are getting? $1976. Is this answer same or
1972.81.
correct? Okay. Watts. All are getting same, right? Yeah.
I'm getting 1976.
Yeah. The answer is 1976.81.
Yes, sir.
Please check it once again. 1976 is, I am also getting 1976. Motor output. P out is equals to input minus losses. Yes. 24,200 minus 1976.81. It is 22,223.18.
Yes, sir.
Therefore, efficiency is P out by P in. That is equals to 91.83%. 91.83%. So in the second case, we have to connect the field circuit separately with the same currents, with the same field currents and same line currents. Okay. So we'll take second case here. Field current, field directly connected to supply. fields directly connected to supply. Okay. So with this, what we get is the circuit connections will change and also the equations will change, especially for the stray losses. So 220 volts. In this connection, generator actually behaves like separately excited one. Okay. So this is 2.5 amps. This is 3.1 amps. They will remain same. Yeah, the line current remaining same. Okay, that is 18 amperes. Line current taken from the supply is 18 amperes, and generator line current is sorry. What is the line current of generator we got there in the previous case? I2 plus I4. Sorry, I2. I2 was 92 amperes. Okay, so this is the line current of the generator. Okay. So this is 92 amperes. But here, 1 second, not 92 amperes. So the given current is for motor, right? The motor current is 110 amperes. So the motor current is 110 amperes. So this is 110. But obviously this will be 92 only. Okay, so this will be 92 amperes. It won't change. Okay. Now earlier the line current of the motor was 110. Now the armature current of motor is 110. Why? Because field is separately given. Field is separately excited. So all the current, line current, what it is given to motor, it is taken by the armature only. So this you have to observe. So now here again the currents will change. My I1 is same 18 amperes. I2 92 amperes. I1 plus I2, which is equals to IAM 110 amperes. Now the stray losses will change here. Okay. Then I2 is equals to IAG. Then I3 is 2.5, I4 is 3.1. amperes. Okay. So now I have to calculate stray losses. So total stray losses in the machine is equals to V into I1. So this is supply voltage V minus, okay, armature copper losses in motor IAM square RA plus IAG square RA. Only this much, because field losses are separately given. Sorry, field currents are separately given. So the copper losses, those are existing in the motors, are armature copper loss and brush contact loss. But brush contact loss information we don't know. Hence we don't use that. Okay. So this is equals to 220 into 18 minus IM is 110 square into 0.05 plus IAG square is 92 into 0.05. This formula is right, huh? We are using the same formula. This is equals to it is 2931.8. Am I audible? Is the connection intact?
Yes, sir.
So therefore, stray loss in each machine WS is equals to WST by 2. Is 1465.9. I will take 1466 watts. Okay. Then motor efficiency. Now I have to calculate the efficiencies of motor and generator. So motor input Pin is equals to V into I1 plus I2. V into I1 plus I2. So that is 220 into 110. So this is 24,200 watts. Motor losses WM is equals to motor copper loss IM square RA plus field copper loss V into I3 plus stray loss WS. So this is 110 square into 0.05 plus 220 into 2.5 plus it is 1466 equals to 2621 watts. Therefore, motor output P out is equals to P in minus Wm. So 24,200 minus 2621. It's 21,579. Watts. So efficiency here only I will find efficiency of motor is equals to directly I will write 21,579 divided by 24,200. 89.16. So previously the motor efficiency was 91.83. Okay. But when I change the connection, the line currents will also change. But here the condition given was line currents will remain same. So for that efficiency decreases. So when I take the proportional line currents, then my efficiency will become same. There is no change in two connection efficiencies. Okay, because we are keeping the line currents same. Okay, then we are getting a different efficiency. Generator efficiency. Generator efficiency you calculate. Okay, you do it as homework because we know how to generator output losses you calculate, find the efficiency. Okay, we'll move to next test because it will be repetition. That's it. Okay. So the next test what we'll be dealing is on the series motor. Okay. The next test what we are looking into is field test on series motor. This is also an experiment in the practicals to be conducted. Okay. So this test is also a direct test. Okay, it is direct test. So whatever the performance parameters we get it at load condition only. Okay. But here also we need two machines. We need two machines. One operated as motor. Other as generator. Okay. Sorry. But one thing here is how it is different from any other test is the field winding of both motor and generator are connected in series. Okay, here field windings of both motor and generator are connected in series. So that both are excited equally. So that both are excited equally. Okay. So the circuit diagram again here both the motor and generator are coupled, which are mechanically coupled. Okay, two machines are used. Two machines are used. One operated as motor, other as generator, which are mechanically coupled. So the circuit diagram goes like this. So this is mechanical coupling, and this is the series field of motor. Okay. So this forms the motor, a series field and an armature in series with that. Okay, which is connected across the supply. And generator field. So this is generator field we have. So generator field is connected in series with the motor. Generator field is connected in series with the motor. So this is the supply voltage V. Supply voltage V. And the output of generator, because generator generates electrical output. So the output of generator is connected across the load. RL. Okay. Output of generator is connected across the load RL. So this is the circuit connection for the field test. Okay. This is the circuit connection for the field test. The principle of this test is, see, the principle of Hopkinson test is to achieve back-to-back connection and the regeneration of output power and only drawing the loss amount of power from the supply. That is its principle. So the principle of field test is that equating the iron losses of both the machine and friction losses of both the machine by providing equal excitation. The main principle of this test is equating, making the iron and friction losses of both motor and generator equal by providing equal excitation. That is the reason why the field winding of both motor and generator are connected in series, so that the same field current flows in the field of motor as well as generator and equal excitation is achieved. Okay. Here we can write here iron and mechanical loss are made equal iron and mechanical losses of both machines are made equal by first thing iron losses are made equal by equal excitation. Okay, equal by providing equal excitation by providing equal excitation. By connecting generator field in series with motor. Okay, so generator field is connected in series with the motor. Motor in the sense field as well as armature. See, in series motor, field and armature are in series. Second, so by doing equal excitation, I will be ensuring the iron losses are equal and mechanical losses are equal by are made equal by mechanically coupling motor and generator. Or mechanical losses of both both machines are made equal by running both machines at same speed. By running both machines at same speed through mechanical coupling. Okay. By providing this arrangement, then the armature of the generator is connected to the load, electrical load. Okay. Armature of generator is connected to electrical load. Then once I start the motor will give mechanical input to generator. Generator will start the generation of electricity. Okay, because the moment I start the motor, the moment I close the supply switch, the fields of both machines are getting the same excitation. Okay, so I will be adjusting the speed of motor with the rated value so that the generator starts generating the voltage, and I will vary the load on the generator. See, here only I can vary the load on generator. I can vary the load on the generator until motor reaches its rated current. I will vary the load on the generator until the motor reaches rated current. Okay. So here what I can say, operation okay. Motor is started. Okay. And made to run at rated speed. Okay. Made to run at rated speed. Okay. Then the load is varied on generator. Load RL on generator is varied until motor draws rated current. Until motor draws rated current. Okay, and we note down all the readings and we do the calculations. Okay, so now here let I1 be the motor current, V be the supply voltage. See, now observe the motor is only field plus armature. The field of generator is an extra connection to the motor. So voltage across motor is not equal to the supply voltage now. Okay, supply voltage is the voltage across series field plus armature plus series field of generator. Now generator is separately excited generator here. Generator is not a series generator. Motor is a series motor. So generator is a separately excited generator. Now the motor voltage is different, supply voltage is different. So let me take the motor voltage by connecting a voltmeter across the motor. And let this be V1. Now V1 is the motor voltage, whereas V is the supply voltage, which is also including the voltage of generator field. Okay, then the generator current, let it be I2, and the generator voltage, let it be V2. Okay, let me take the computations. Let V be the supply voltage, V1 with the motor input voltage, so the motor voltage is taken across the field and armature in series. Okay, so that is only the motor voltage. Then I1 motor input current, okay, motor line current. So in series machine, line current, armature current, field current all are same. I2 generator line current or armature current, because they both are same. Then V2 generator terminal voltage, and RA with the hot resistance of motor and generator. Again, we assume both machines are identical. Okay, we assume here both machines are identical. Okay, so here what I can say is, what is the total input to the MG set? Line current is V volts, line voltage is V volts, line current is I1. Is it? Yes or no?
Yes, sir.
The current drawn from the supply is I1. The supply voltage is V. So therefore, the input to MG set input drawn from supply by whole set is equals to, it is V into I1. Okay, then what is output? The grand output of the set is output of generator.
V2 into IL.
Huh? Hey, V2 into RL.
IL into IL.
Okay. So the grand output is the output of generator. Input is electrical, output is also electrical because it is MG set. Okay. So output power developed by set is equals to V2 into I2. Now, when I deduct V2 I2 from V into I1, do I get the total losses in the set? Therefore, total losses in set is equals to input to set minus output offset. Okay, so that is equals to V into I1 minus V2 into I2. V into I1 minus V2 into I2. So this is the total losses. Okay. Let me take it as WT. Now, what are the copper losses in the set? Now I want stray losses. Now I know total losses. If I deduct all copper losses in the set, I will get total stray losses of the set. Copper losses in set, in whole set, is equals to, okay, motor armature copper loss plus motor field copper loss plus generator armature copper loss plus generator field copper loss. Okay, so this equals to, so motor armature copper loss, the current in motor armature is I1. So it is I1 square RA plus, if we know exactly the voltage across each field, I can take that voltage multiplied by current I1. If I don't know, then I have to find the resistance of field winding, RSC. Okay. So let this be RSC. Let this be RSC. Here I have RA and here I have RA. Okay. So I can write this as I1 square RSC plus generator armature copper loss. Armature current of generator is I2. So I2 square RA plus generator field copper loss. Observe, the generator field is connected in series with the motor. So the current flowing in the generator field is I1, not I2. So it is I1 square RSC. Okay. So I can write this as I1 square RA plus I2 square RA plus 2 I1 square RSC plus 2 I1 square RSC. Therefore, total stray losses in the set total stray loss WST is equals to, I can write total losses minus total copper losses. So this is equals to WST is equals to total losses are V into I1 minus V2 into I2. That is WT. Let me take this as WCU total. WCU total. WT minus WCU total. Total losses minus total copper losses. Okay. Therefore, stray losses in each machine WS is equals to WST by 2. Assuming stray losses gets equally divided between two machines, because we are using identical machines. Again, this is as a full load test. I am calculating stray losses. Okay. So how to find the efficiency of motor and generator, we know already. Okay. That we'll take in the next lecture. Now I will end this lecture here, as it is time of for the second next lecture. Okay.